Have you ever really thought about what happens right after a medication is injected? I mean, it hits the bloodstream and then what? Its journey through the body starts right then and there. And you might think it's a simple process of fading away, but it's actually a fascinating two-part story. Let's break down exactly how it works.
So let's start with a really basic question. A drug goes directly into your blood. Your body, immediately starts working to clear it out. If you were to draw a graph of the drug's concentration over time, what do you think that would look like? You'd think it would be a straight, steady decline, right? Just a smooth, constant removal process. But the reality is so much cooler than that. Instead of a simple straight line, what scientists actually see is this curve. It has this really steep drop at the beginning, and then it's followed by a much, much gentler slope. So what on earth is going on here?
Well, pharmacologists have names for these two parts. That first big plunge, that's called the distribution phase. And that slower, steadier decline after it, that's the elimination phase. Understanding this two-part process is really the key to everything. And it's the puzzle we're going to solve right now.
Okay, to get this, we have to put on our pharmacologist hats and use a model. Our story really kicks off in what's called the central compartment. Think of it as the drug's grand entrance, its very first stop on a tour of your body.
Now, here's the crucial thing. This isn't a literal physical box somewhere in your body. The central compartment is more of an idea, a theoretical space. It's made up of your blood and all the organs that get a ton of blood flow. We're talking the big ones, like the heart, liver, and kidneys. It's basically anywhere the drug can get to and spread out super fast.
Here's an easy way to picture it. Imagine a huge central train station in a city. All the passengers, in our case, the drug molecules, they all arrive right there in that bustling hub first. From there, they start their journey out to all the quieter, more distant neighborhoods. And this table really shows you the difference between that central hub and those outer neighborhoods. The highly perfused tissues, heart, brain, kidneys, liver, they're like the major downtown metropolitan areas of your body. They get a massive amount of blood flow. But the slowly perfused tissues, like your skin, muscle, and fat, they're kind of like the suburbs. It just takes a lot longer for the drug to get all the way out there. So, how does this whole city and suburbs idea explain that first part of our graph? Well, this is the story of that initial steep drop, what we can call the great drug distribution.
Okay, remember that crazy steep initial drop on the graph? That's the distribution phase in action. And what you're seeing is not just the body getting rid of the drug. Not at all. It's mostly the drug leaving the central station, the blood, and just rushing out into all those other tissues, all those neighborhoods we were just talking about.
And hey, don't just take my word for it. This quote from the source material nails it. The big takeaway is that first huge drop you see in a blood sample, it's all about movement, about relocation, not just removal.
All right, so if the first phase is just the drug spreading out, what happens next? What's going on in that second, much gentler part of the curve? This brings us to the slow fade of equilibrium and elimination. So after that initial rush, things start to quiet down a bit. The drug starts to find a balance, a kind of harmony between the blood and the outer tissues. This is what's called distribution equilibrium. The drug is basically settled into all the neighborhoods, and the movement in and out starts to even out.
And once that equilibrium is reached, the whole shape of the curve changes. This gentler slope is the true elimination phase. Now the main reason the drug concentration is dropping is because your body's amazing filtration systems, we're talking mainly the liver and kidneys, are just steadily and systematically cleaning the drug out of your entire system.
Okay, so we've got the theory down. It's a two-step process. But why does any of this actually matter? Let's look at a real-world, high-stakes example to see how this isn't just an academic exercise. This can be a matter of life and death.
We're going to talk about a heart medication called digoxin. Now, digoxin is an incredibly powerful drug, which means getting the dose exactly right is absolutely critical. And understanding this two-phase journey is the key to using it safely.
Just look at this simulation. It's pretty stark. On the left, you've got a patient with normal kidneys. On the right, a patient with renal failure. Now focus on that patient with renal failure. See that top line? That represents the amount of the drug building up in their tissues. It is dramatically higher and it stays dangerously high for much, much longer, all because their elimination system just isn't working properly. And to put a really fine point on it, look at this number. After just 8 hours, a patient with renal failure can still have over 181 micrograms of digoxin built up in their body's tissues. That is a potentially toxic level that this model helps us see coming.
And this is exactly why this model is a potential lifesaver. It lets doctors estimate how much drug is in the tissues, places they can't actually take a sample from. It proves to them that a blood test taken too early during that distribution phase will give a dangerously misleading result. And most importantly, it gives them the information they need to adjust the dose for patients whose bodies can't clear the drug well, preventing a toxic, dangerous buildup.
So, it all comes back to this, doesn't it? We started with a simple curve on a graph, but what we uncovered was this incredibly complex journey of distribution and then elimination. It just goes to show you how a seemingly abstract mathematical model can give doctors the critical foresight they need to turn a powerful medication into a healing tool instead of a harmful poison.